Now with more coffee, J.Roe is going to talk us about the last development in Lustre, which some, if not many of us use in our clusters. So, Adam?
Thank you. Can everyone hear me okay? Right. So, my name's J.Roe. I'm a HPC solutions architect for Intel, and I've kind of come here today just to explain the situation and what's going on, because some of you may have heard some announcements that Intel made about Lustre not too long ago, and I just wanted to come here today to reaffirm Intel's commitment to Lustre and what we're doing in terms of moving forward technically and also strategically as well. So, just for a quick high level, for those of you who don't know what Lustre is a parallel distributed file system. It's one of the biggest file systems in HPC and used across many, many systems within the top 500, among other in not necessarily HPC-oriented workloads, maybe the enterprise as well. So from a high level, it's very, very scalable, very, very parallel. Scales up to 512 petabytes with the HDFS backend, but if you use the ZFS backend, which is a direction we're going in, which I'll talk about shortly, you can grow to exabytes essentially. So just from a high level, this is where we're positioning. So we made a statement maybe about 2 months ago now saying that we're changing strategy on Lustre. So Intel historically had their Intel Enterprise Edition for Lustre releases, plus a number of other releases. Moving forward, we're going to a completely community-oriented model. So Intel is still fully behind the product, fully behind the technology, committed from an engineering perspective as well, but we're going to be open sourcing the Intel Enterprise aspects and going completely to a open source plus maintenance release model. So this means that the 2.10 release, the next release coming up, will be a long-term supported release, a bit like an Ubuntu style model, which Intel will be supporting and providing maintenance releases for. The main reason for this was that we're going to allow us to put more commitment and more engineering effort into a single release. So historically, Intel was maintaining maybe 4, maybe 5 releases. This is allowing us to commit all of our engineering effort to one single release. So we get features out quicker, we get the file system in a more stable place, and we get everyone basically happier. So from our side, we don't feel this is going to impact partners or customers in any way, purely because they're still getting the same Lustre file system of a higher quality and of more features. It's a bit dark. So from a community roadmap perspective, this is where we're at. So those of you who are familiar with the Intel releases, we are using the Lustre 2.7 release. Yes?
Sorry for interrupting. Could you please go back to the slide? So here what you're saying is that Intel is going to give the enterprise part to open source it to the community, which is going to be development from Intel side and from the community, and Intel will be delivering support.
So, in a sense, yes. However, it's important to note that the Intel Enterprise release that we had before was never a closed source. So there was parts of it, like the Intel Manager for Lustre, which are going to be open sourced. But all of the bits were fully open source. It was just basically the recipe that gives you a stabilized version. So we're not open sourcing, we're not going to open a GitHub tree which says Intel Enterprise for Lustre. We are basically committing our engineering resource and all of the patches and features into the mainstream release. So all the work we've been doing, we're now putting directly into the community release. So the 2.10 release coming out in back end of June will be basically the first release where Intel isn't, we're not doing the enterprise model, so we're doing community-only release.
Yeah, okay, so there are no more two versions, it will be only one from the community.
Correct, yes. And this will be then supported by Intel.
Okay, and do you have some contracts for support, or it's also supposed to community?
So I didn't want to touch into the commercial side of this, really, because that's not what it's about. But from a high level, any contract that's pre-existing is completely honoured to the duration of the contract, and any renewals are then negotiated afterwards. And so moving forward, support contracts will take place as they did before with, like you saw with Intel Enterprise Edition for Lustre. So you can still get support contracts, you can still do all of those things as well in the same way that you did previously. Okay. Any more questions before I move on? Is it clear? Okay, so from a community roadmap perspective, this is where we're at. So 2.9 got released not so long ago, and we're launching 2.10 at the back end of June. So one thing that's important to note is if you're aware of how we do Lustre releases, a lot of the features which you see in the mainstream aren't available in the enterprise release. So this is, again, another motivation for going to this model, to allow us to get more features and get people to use these features quicker. So as of the 2.10 release, you're going to see a lot of new features coming into the enterprise, community product compared to what we had in the enterprise release, purely because this is allowing us to do this now. So the 2.10 release, which is coming out, ZFS snapshots is something which you saw in the enterprise release. This is going to be moved into the 2.10 release, so you can do asynchronous snapshots of the entire file system. This is going to be available on the community as of 2.10. Multirole LNet is a development which is being worked on by Intel and SGI to basically allow you to get more bandwidth out of a system by doing RDMA bonding on the Lustre network layer. I'll talk about this in more detail a little bit. This is just a high-level roadmap. Progressive Fileouts is something which is extremely interesting. This is essentially allowing you to not have to worry about doing striping anymore. So this is basically policy-based file system striping. So you can essentially set I'll explain later, but you essentially set a size threshold, and the file system will automatically stripe that file based on the size threshold. So it optimizes for workloads essentially without you having to worry too much about what users are doing on the file system. This is sort of accommodating for these new mixed workload clusters, because we're seeing a lot of people move away from traditional HPC to these kind of mixed workloads with data analytics, machine learning, all the types of workloads which have different data requirements. So progressive Fileouts is certainly a feature which can support that and allow that to work better on HPC type environments. Project quotas is basically directory quota. This is coming in the 2.10 release. This is something which has been requested of us for quite a while now. So Lustre will be file and group quota, user quota, and then as of 2.10, directory quota. Moving forward into 2.11 and 2.12, as you can see, the features thin out purely because we're not sure what to commit to yet. But from a feature perspective, data and MDT is extremely interesting. This is allowing us to write data directly on the metadata targets, because if you're familiar with the Lustre architecture, you essentially you split your metadata and your object data. So if you're writing small files, let's say, I know, a 4K file, to talk to the MDT to write 2 or 3 Ks of metadata to then go and talk to some object servers to write that 4K of data isn't very productive. So data and MDT is essentially allowing us to write directly to the metadata target. So that's something which is coming in the 2.11 release. I'll talk about it a bit later. So this data is a little bit old. This is just basically an adoption where we position, where we see Lustre in the top 500. So this is on the left-hand side is an analysis of the top 100. This data is about 2014, but the newer data shows Lustre is about 75% now. And some of the other numbers have shifted around a little bit as well. But we are the predominant file system in the top 500. If you look at the entire array of systems, it's about 55–56% are using Lustre. From our side, we see this as a very positive thing. Obviously, there is other file systems out there, and they all do a very good job. It's just a case of where the market sits, and we see this as the trend at the moment. 9 of the top 10 sites on the top 100 are all using Lustre as well. From an Intel contribution perspective, this is what the unique contributions look like. You can see Intel's contribution is just over 50% of the code base to Lustre. The rest is all from industry or other commercial partners. This actually shrunk from the previous Community 2.8 release, which from our side is a good thing. This is showing adoption within the community and other unique contributors to the product and to the Lustre release. So there's obviously there's the likes of DDN, Seagate, there's your big commercials, but then you also have academic institutions as well who are also contributing to this and adding features and also bug fixes to the code. And we see this as a very positive move, and we see the community growing from the Lustre side. I won't talk about this too much. This is just Intel partners for Lustre. So from a high level, I won't talk about this because we want to talk about the features, but for those of you who aren't familiar, this is from architecturally what a Lustre file system looks like. You split your metadata, you split your object data, and then you have some form of management server to interpret the data and basically to get some statistics from the file system. It's important to note that the Intel Manager for Lustre, which was the commercial offering, is now being open source. So that will be available on GitHub within the next few weeks for you to download, change, and do what you will with. I mean, there's been a lot of other open source tools which allow you to monitor Lustre file systems available for quite a while, but the idea is we're putting Intel Manager for Lustre on the community as well, so you can download this and do what you like with it. So Lustre with ZFS. This is sort of the direction that we're going in. So historically with the Lustre file system, you would typically have hardware-based RAID arrays. You would be limited to the performance of the controller, and you'd be limited to the feature set of that. ZFS gives you a lot more opportunities in terms of features, but also performance. So generally the motivation is to accommodate some of these new usage models. I mean, if we look at, for example, genomics, a lot of genomics workloads take advantage of compression quite heavily. So how do you get compression on an LDiskFS-based file system? It's quite difficult. So using something like ZFS in the back end, which inherently has compression capability, why don't we leverage this? So looking at all these use cases, ZFS is allowing us to scale not only beyond what we can do today, scale us to the exascale, but also give us a lot more features and a lot more functionality to the file system. So I mentioned compression. I'll talk about that in a little bit. Data reliability is one. So with ZFS, you have always consistent on disk. You always have checksums from basically the server all the way down to disk. If you look at a hardware-based or a traditional file system, essentially you're at the mercy of your storage controllers. So as soon as the data hits the storage controller, you basically say, acknowledge, that's fine, and it's there. However, you're never sure if that actually is the data you've written is the data that you actually put on the controller. So ZFS is talking right on disk. So you have checksums all the way down to before the data is written on disk, and then you have always consistent on disk to provide, to mitigate any bit rot for kind of long storage data. Snapshotting is something which is also very interesting. So a ZFS-backed Lustre file system gives you the capability to do snapshots. You may think, well, ZFS, you can do snapshots and you manage them, but that's not what it is. So essentially, it is a synchronous Lustre snapshot. So at any given point, you can essentially tell the file system to snapshot, and you can get a persistent point in time leveraging ZFS, copy on write. It allows you to get a synchronous snapshot of the file system. You can then mount this snapshot as a different namespace, as a read-only namespace to do persistent backups from, to do accidental deletion protection, data recovery, that sort of thing. So whereas if, for example, you wanted to back up a Lustre file system today, you would maybe take 2-3 weeks to back up a several petabyte Lustre file system. Over that period of time, the data could have changed significantly. Using snapshots essentially allows you to guarantee a persistent point in time which you can back up against or recover to, if need be, without having at the mercy of, let's say, how long it takes to do the backup. Hybrid storage pool is one, so allowing you to get basically more IOPS from a file system. You can use SSD caching without having to buy expensive proprietary RAID keys or that sort of thing. You can leverage basically just a SSD to cache data on your storage servers. Manageability is one we're working on, so we're working on a few things for ZFS Event Daemon to allow ZFS to become more easily manageable. And because it's all in the user space, it's very easy to manage from a file system perspective, as opposed to having to rely on accessing storage controllers directly with different management interfaces depending on who your storage vendor is. So it's allowing you to have a more generic Lustre solution by gaining more performance, but also getting a lot more capability. Industry adoption, I tried to get some statistics for this before I arrived, but I couldn't find them in terms of what percentage of Lustre file systems are using ZFS. But just some examples that are using it. So for example, Lawrence Livermore has used ZFS right from the get-go. They've been using Lustre plus ZFS for the past 2-3 years now. Plus a number of other sites as well that have gone in production using Lustre and ZFS. Pittsburgh Supercomputing Center is an example as well. So it's certainly a growing technology, and we feel that moving forward, it's the direction we want to go in for the path to exascale machines. Some of the work on ZFS. So as I mentioned, there's a handful of features which are included as part of it. If we look at, for example, native encryption, this is on one of the kind of other ZFS trees, but as part of the open ZFS tree, encryption at rest is something which is being brought in. So this is something which you can leverage on Lustre. So encryption at rest can be useful for those sensitive, pick a use case. I mean, some people have a requirement where they need encryption at rest, they need encryption on their storage. And you can use, for example, Kerberos in Lustre to get encryption on the wire. You can then use encryption at rest with ZFS, and then you've got a more secure file system, let's say. Parity acceleration is one. So essentially, we funded some development within ZFS to allow us to accelerate parity calculations. So with ZFS, you're doing parity calculations on the host. You're not doing it on a RAID controller. You're doing it on the CPU. So as part of that, we're actually allowing us to leverage the instruction sets of the Intel CPU, so the current and next generation Intel CPUs, to accelerate the parity calculations, to make things like write performance faster on arrays. So to make the read-write parity with a storage array basically the same. I mean, if you look at a hardware-based RAID controller today, you'll probably see your traditional RAID 6 array, your read performance is probably double your write performance. Moving forward, RAID Z2 with parity acceleration using the host CPU, you can get basically on par read-write performance with your single array. Another interesting one is probably decluster RAID and plus a number of other things, so fault management, performance enhancements. These are all things which we're working on for the next generation of machines, so basically just ZFS enhancements. We really see this as a direction moving forward to scale the file system and get us more performance, and these are all individual components which are going into the ZFS. We have developers which are actively contributing to the OpenZFS project. One important thing there is IPCC, so the Intel, basically Parallel Computing Centers. This is a funding opportunity from Intel where they essentially put funding into academic institutions and research institutions to fund development in certain aspects of things. So it could be to optimize code base X on the latest generation of CPUs, but it also could be, for example, create this feature for Lustre or create this feature to allow us to leverage this technology. These are things which is actively ongoing and where Intel's contributing back into the community to develop these feature sets to work well on the products. So let's talk about some of the technical features from a slightly deeper level. So ZFS snapshots is an interesting one. I mean, I've spoken about this just a minute ago, and it's something which has been in the enterprise product for quite a while now, but it's something which is new to the community. As I mentioned, this is basically a synchronous snapshot. So you can really take advantage of this by doing, quick undo and delete rollback. This isn't just necessarily, you do a snapshot and a sysadmin has to mount it. This can be mounted at anywhere within the network. So a user could say, oh, I've deleted something. They ping a sysadmin saying, could you mount a snapshot for me? They mount it to some client X. They can then recover their the data which has been deleted. I use the use case of backup, which is something which we've seen ZFS snapshots being talked about heavily for, purely because the problem with backing up large file systems is it could be quite difficult to get a persistent point in time to back up against. ZFS snapshots is guaranteeing that by leveraging copy on write on the back end of ZFS to make a persistent snapshot, you back up against that and you have a consistent data essentially to back up with, to restore if need be. Security is one I touched on Kerberos briefly. So Kerberos is allowing us to do on-the-wire encryption. So this is something which has been, leveraged by some of our government customers and also leveraged by people in kind of the defense space who want that level of extra level of security. So using things like Kerberos, which gives you encryption on the wire, as well as SE-Linux on the client side, to basically support those features. Another thing to mention as well, sorry to go forward, is a few things which are being developed around security. So Lustre has traditionally been a HPC file system. People have seen it as a scratch file system. There's a few features which are in development that are basically allowing us to act in a more multi-tenant type environment. So for the people who want to run things like OpenStack, for the people who want to run containers, that sort of thing, it's allowing us to create basically containerized file systems within a single HPC file system. So you can leverage basically Kerberos, UID GRD mapping, SE-Linux support, plus the share key crypto technology, which is being worked on by a handful of other people, and also the data isolation, which DDN is working on, to allow us to create containerized file systems within a single Lustre instance. So you can run your OpenStack cluster on top of Lustre, for example, without having to worry about data being made available to people who it shouldn't be. So that's something which is quite interesting, something that's being worked on quite heavily. Yes.
That's also regarding the containers here. Does that mean that we can replace, for instance, Ceph by Lustre, and through Swift I can write to the backend?
So you can't necessarily. So with Lustre we have connectors for things like Hadoop, but you can't necessarily enter, depending on what your application is. You need to be able to talk POSIX to be able to do it.
Okay, so that's one of the, because there I need an object store.
Yeah.
I don't speak object store. That's what we
Yeah, so you need to be able to talk POSIX or you need to be able to talk HDFS because we have adapters for Lustre which talk HDFS. There's some development work going on for the DAOS project, which is something which is a long-term development for the Exascale projects, which is an object store. So future, yes, but today, no. I did mention it briefly, the Hadoop adapters. So this I'll touch on briefly because these haven't received much love, let's say, over the years. So this was a good time to do it. As part of the open sourcing effort, we're open sourcing our Hadoop adapters. So this is allowing you to talk to a Lustre file system with HDFS. So you can take your big data cluster and talk to a single parallel file system without having to necessarily split your storage up between many compute nodes. So this is, again, one of those development efforts which is allowing us to exist in multi-workload type environments. So let's say you're procuring a cluster. You don't need to procure a big data cluster plus a HPC cluster. You procure one cluster and then use a common file system. This is not only allowing you to basically consolidate resource, but it's giving you better performance as well. With HDFS, there's a shuffle phase where you translate data between the nodes. Because this is on a single parallel file system, you avoid having to do the shuffle phase. So essentially, you're getting good performance on a single common file system. So for example, you can do your HPC compute job and then do some analytics on that afterwards on the same environment within the same scheduler environment, because we have the adapter for MapReduce as well, which is allowing you to schedule Hadoop type workloads within a HPC scheduler. I've spoken about this. Multi-rail LNet is an interesting one. So I've spoken from a high level about what multi-rail LNet can do. I mean, if you look at storage systems today, if you want high bandwidth, you need to do bonded Ethernet. You can't bond InfiniBand, right? So multi-rail LNet is allowing you to actually do that. So you can bond RDMA links within a Lustre environment. So with if you look at MPI, you can kind of essentially do bonding by routing the MPI in a multi-rail kind of environment. But when you talk to storage, you can't necessarily do this. So multi-rail LNet is allowing you to aggregate, basically in a round-robin fashion, multiple Lustre network interfaces. So it could be to OmniPath interfaces, to InfiniBand interfaces, to RDMA-capable Ethernet interfaces, into a kind of a single virtual link, which is allowing you to get better bandwidth into the systems. There's two reasons why this is useful. So the first reason being shared memory machines. If you look at some of these big shared memory machines, I won't mention any specifically, but if you want to do RDMA or InfiniBand into it, for storage, you're basically tied to the single highest bandwidth link you can, which is 100 gigabit Mellanox CDR or Intel OmniPath. To scale this, if you want more bandwidth, you need bonded Ethernet. What this is allowing you to do is to get 4, 8, 16, or maybe more RDMA-capable InfiniBand interfaces into a shared memory machine to get the performance for the storage over a low latency, high bandwidth link without having to sacrifice latency for Ethernet, for example. So this is certainly a very interesting feature that's allowing us to become more relevant in that space. If you were to look, for example, at the way storage technology is going, you look at the NVMe, for example, extremely fast devices. If you put maybe 3, 4 NVMe devices in a single box, there's enough bandwidth there to saturate your network link. So what happens if you want a storage system which has very, very high bandwidth, but you need the network capability to do it? You can use multi-rail LNet to basically get all of that bandwidth out of a storage box or into a very large client with many thousands of cores. So it's an extremely useful technology, extremely interesting technology, which is allowing a lot more possibilities. It's important to note as well, the links also support failover, which you would expect as well. So even if you wanted, redundancy, you could essentially create redundant links without necessarily taking advantage of multi-rail LNet. Go ahead.
Okay. So I have multiple routers.
Mm-hmm. You can do it on LNet routers as well, yeah.
Okay, so that's where I can get the maximum.
Yeah, because exactly, yeah, because your LNet router today probably looks like a single 1U box with one interface and another interface. So if you want to leverage the system more, you could put, maybe 3, 4 in, 3, 4 out, and get the bandwidth out of a single router, so you get basically better cost of ownership. Data and MDT I'll talk about briefly. So I did mention from a high level, this is basically allowing you to write directly on the metadata target. This is an extremely interesting technology for these kind of new AI type workloads or these new mixed workloads where you don't necessarily know what the I/O requirements are, and you also want to get better performance. I use the example of writing a small 4K file where if you write it to object, you still need to write the metadata, which is probably the same size. So doing those RPCs doesn't make much sense. So we're basically allowing you to write directly on the MDT. Combining this with something like progressive Fileout, which I'll talk about in a minute, is allowing you to scale the file system and get better performance. So these are just some examples of basically workloads which you would see from an I/O perspective on a Lustre file system. It's basically making a 3 RPC workload a 1 RPC workload. So instead of doing, talking to the MDS, getting a transaction back, then talking to the OSTs to write the data, you can do it in 1 RPC, basically write it on file open and write directly to the metadata target. And this does translate into real numbers. So this is working code. This, again, is in the master branch, but it won't be in the 2.10 release if it's coming in the 2.11 release. So this is an example of real numbers. So just ignore the orange graph for a minute and compare the blue and the green ones. So the blue one is a traditional Lustre file system. So it's an NVMe metadata target plus an OST, and then writing 4K workload. So I wrote X number of 4K files to see what performance I got. I got 20,000 file creators per second of 4K files, which is fine, it's modest, but keeping in mind you're writing data. So I mentioned before it's taking a 3 RPC workload to a 1 RPC workload. If we then leverage data and MDT and write directly to the metadata target, you actually get 3x boost in performance compared to the green line. So the green line is using data and MDT with exactly the same configuration. The client is writing directly to the metadata target, and they've got 3x improvement in their metadata performance and small file performance. So for workloads that use small files, you can essentially guarantee 3x performance improvement on your I/O. So it's an extremely compelling technology. And it's coming soon within the Lustre release in 2.11. Is there any questions on that before I move on? Probably a lot of information. Okay. Progressive fileouts, or composite fileouts, how it's called here. This is policy-based striping. So it's important to note that the bottom right-hand corner, this is an example only. It could be whatever you want it to be. But the example here is one stripe is 0 to 32 meg. So in the ideal world where you're leveraging data and MDT, this basically means any file you write to the file system, the first 32 megabytes is written directly to the metadata target. This is something important to note because that means if you're designing a system, you need to make your MDTs bigger. You may need more MDTs, but it is allowing you to get more performance. After that, the next 4 stripes go to OSTs. So if your file grows beyond 32 meg, the rest of the data is then striped for OSTs. Beyond that, it's then striped to 128 as in this example. So it could be whatever policy you want, but this is how, basically in practice, how it's working. It's policy based on size. As the file grows beyond X size, it is striped to more OSTs. The final one is probably file level redundancy. So this is probably the last feature I'm going to talk about from a high level. This is something which is coming in the future. So 2.11, there's two versions of this. There's the asynchronous version and the synchronous version. The asynchronous version coming in 2.11 at the back end of this year is basically an after-the-fact mirror of the data. So essentially, you'll write data to your Lustre file system. You can then define you want to move it to somewhere else. So you can essentially do a RAID 1 over network after you've written it. So you could basically make a replica of that data somewhere else within the Lustre file system. So for example, should you lose an OST, should you lose a disk array, that data is still physically present. You essentially just get a cache miss and it goes and reads it from somewhere else. This is the asynchronous one, which to me isn't that interesting. The more interesting one comes when you get to the synchronous one in 2.12, which is basically you do a RAID 1 over network at write time. So you get a write commit from both parts of the storage. So essentially you get mirrored storage. This is allowing you to, the people who do, for example, multi-site, who want replication, it's allowing you to do replication within a Lustre file system, essentially. So that's, again, an interesting feature. It's still in development as to what it's going to look like for sure, because there's a lot of elements in there. You need, for example, policy engines. You need a few other things like that to get the data moved around correctly, but it's certainly a very interesting technology. And for me, that's about it. Did you have any questions? Snapshot, yeah.
Yeah, that one. Can you develop a little bit more on this feature? What exactly do you need to do? Do you need to freeze the file system before taking the snapshot? How long does it take?
Yeah, exactly. So there's basically a blocker. So for any I/O commit on a Lustre file system, you need to talk to the MDT. So as soon as you issue a snapshot, you have to issue it from the MDT. It puts a blocker on the MDT to stop you from committing new data. Because it's POSIX, if your application is trying to write data, it will just wait. But it's basically instantaneous. There may be a couple of seconds where it pauses, but it's pretty much instantaneous. So it basically puts a blocker on the MDT, triggers a snapshot at the Lustre level, which basically goes off and synchronously snapshots all of the other OSTs, combines them into a single snapshot, and then that's made available on the file system for you to mount.
Do you have data on the largest size of file system that you have? That this feature has been tried on?
I can probably find some, but I don't have any immediately. It's been within the enterprise release for about 8-9 months now. So anyone who's using Intel Enterprise for Lustre 3 or above has this functionality, and it's going to be in the 2.10 release. So I imagine I can get some data quite easily.
Okay, thanks.
So then there are no more questions. Thanks again.
Thank you.